overview of the instrumented system, and it's got basically two parts. I divided this whole lecture into two parts. Presentation. Part one, you may find it a little unconventional. It's called a mock design of a hypothetical safety instrumented system. Now, why I'm doing that, people will say that without giving a proper overview introduction, why are you doing that? I'm doing that deliberately because I tested this method in one or two places and it seems to be okay. Now, this design, which all of us are going to do, the participant and myself, in a virtual kind of a, atmosphere, is basically going to extract all the key points of definitions, concepts, and various other issues which are going to come in the overview of safety system part 2, which in fact is the main one. So we'll be using, you'll find that we have covered 90% of what we are going to talk in a simplistic way by this method. Now, before I start this, I will go through the routine defining of safety, which all of you know, because you are practicing academicians, and I'm sure there are many practicing senior professionals also. So I'll just read through it. What is our topic? The name is Safety Instrumented System. So we will not talk about instrumented system because we have all been talking about instruments. Safety refers to relative freedom from danger, risk, or harm, injury, or loss to personal and or property, whether caused deliberately or by accident. This is just a definition that basically tells you that you must get relative freedom by following this safety practice from all these things. This is all known to you, nothing new. Another important thing I'm telling you is, what you mean to say safety was not practiced in the years long? The answer is it was practiced. People were serious and people were working in pockets. That is, if the man was operating in a crane or in a process plant or in a ship, everyone followed the rules that was prescribed for that. If you have to wear a helmet, that's called hard hat safety. It was being practiced. It was not that it's not being practiced. But then what happened is, curious enough, there were accidents, there were solutions, etc. But curious enough, in the year 1974, in the UK, in a place called Flixborough, and in that place called Flixborough, it was an ordinary chemical plant. I think they were manufacturing nylon products or something like that. And what happened was, I won't go into long details in that because we need to have a diagram, but I'm talking without a diagram. So there were 5 or 6 vessels doing reaction in series, 1, 2, 3, 4, 5. So one of the vessels developed a problem. So that had to be bypassed. So if you want to bypass, you say 1, 2, 3, 4, and then you go to 6. So this vessel was made into a dummy, and for that they had a well-designed flexible pipe and a proper engineered modification. And engineers were serious. They were not light-hearted when they did it. They checked their mathematics, their physics and engineering and everything, and they put it. But what happened was a very sad thing. While this modification was working for a couple of days, it suddenly caught fire. The place caught fire. Sorry for interruption, Professor. Are you getting my audio clearly?
Yes, sir. Yes, sir. Continue, sir. Continue.
Yeah, because there is some pop-up coming, then I'm not able to hear some other person. So I thought, anyway, I can't do much about it. So it's clear to you?
Yeah, clear to all.
That place was called Flixborough, and about 30-40 people died. The factory was wiped out, and the whole village was wiped out. The Flixborough village in UK was absolutely brought into the ground level here. So what happened was, all the chemical engineers, very senior professionals, the world got together, and then they said, we have to look at safety in a much more deeper way. And you can say, I can tell this very unofficially because I don't think I have the knowledge to talk on this. I could say that the real safety and organized analysis took its birth in that period. And the author of that was Trevor Claes, very well-known person internationally. And he was working for the company called Imperial Chemical Industry UK, the branch of which I happened to be working. And in fact, I had the good fortune of meeting Trevor Claes in one of the meetings. And that was almost like meeting a top scientist. Now, coming to the main point is, okay, we have talked about all this. We have talked about Flixborough. So what is the awareness? So let us do one thing. I'm doing this in a very unconventional way. We are going to, as a group, although we are sitting in different places, we are going to get together and design a safety instrumented system. Now, before I start talking about the safety instrument system, the first hurdle you have to come across, because a lot of experts who are going to be imaginary experts, who are going to be in front of us, are going to ask, do you need a safety instrumented system? So the first question has to be answered. Now, before that, let us actually fantasize that there is a big company and they want to make a product, and the managers, very senior directors, have given a simple sketch. They've given a very simple sketch to you, and we are all the people who are the professional engineers or managers or of all disciplines. The top director has told, I want to make a product C. And the product C is basically an inert liquid which has to be used in pharmaceuticals and maybe in some other special chemical industries. Fine. Okay, that's the end use of the product. It's a liquid. So to make that liquid C, you have to react A and B. A liquid and B liquid. Then, okay, so simple. But he said, no, it's not so simple. The liquid A is a very, very hungry chemical in the liquid form. It is toxic and inflammable. In fact, it had all the inside it. So you have to pump this liquid into this yellow figure reactor and add liquid, then add liquid A and produce. Okay. And each reaction will take about 1.5 hours. And the first, the amount you have to send in is about 2,000 or 2,500 liters. Okay, these figures I got in mind. I know I won't why I'm telling all this, but you accept the figures I'm telling you. So straight away, the people met and they asked, we want to have a proper write-up. This is only a verbal, description. And let's assume I'm the top brass of this company. Then he tells me, oh, I'll tell you. Then the first document that you're going to get in the hand as we people as a design group, he says that the objective to produce a product C by reacting A and B. And all his professionals have told him liquid A is very hazardous, toxic liquid and reacts violently with another chemical as liquid. Then he says, okay, I can give you a few points. Reaction is carried out by controlling pressure at 30 pounds per square inch gauge and temperature of 120 degrees centigrade. Then he says, however, liquid C is an inert liquid, product is safe product, and it's used in pharmaceutical and related fine chemicals. So the overall process narrative has been given. Then the other group takes over. That is the slightly senior people, but they're all qualified professionals. Then they do their, they have a number of sessions, and then they say that the reaction is extremely fast and pressure will rise rapidly. One group says, this is part of the understanding what are the dangers, hazards, and what is the risk involved for that. They say that, okay, we summarize, reaction is extremely fast and pressure will rise rapidly. There have been instances when the explosion has occurred inside the reactor. Design group to note this. Next, liquid air leaks are known to have created a vapor cloud explosion in the vicinity of operation. I'll explain that a little later. Please note that this is a very hazardous operation, and therefore the site has been carefully chosen so that it is as far as possible from residential area. That means what? He's going to take a calculated risk, but a sensible calculated risk. The next one is design group to prepare a proposal of the system bearing in mind the risk factors and how they propose to build in and control and safety of the system. It's a small mistake. Anyway, how are you supposed to build it, control it, and ensure the safety of the reaction system? Okay, point I have not added here. That is, if the reaction explodes inside, so obviously you have to protect the reactor from going into splinters, because you are dealing with a deadly chemical. And we sometime back, maybe about a minute back, I talked to you that vapor cloud explosion. So now I'm going back by one slide to explain this, which all of you know. Everyone working in the academics or in the industry, or any industry, you would know this. That is, this is called the famous red the triangle, the fire triangle. But now they have upgraded that definition. They said that you need oxygen in the form of air, and then you need a fuel, and then you need an ignition source. Ignition source can be a spark, can be lightning, and also can be heat. Very body heat, that chemical which is surrounding this area will not accept, will take it as ignition. And once all the three sides of the triangles are satisfied, a reaction also has to take place. And when the reaction takes place, there could be fire, there could be explosion. Okay, why I'm saying this? Because I talked to you about a vapor cloud explosion. Now, vapor cloud explosion, I will talk about this once we go to the diagrams. So keep in mind that all of you know you need three factors to cause an explosion or fire. And how does one see this explosion? There are thousands of pictures. This is one of the sad events. I don't know which place, but this is how I have seen some factories after explosion. And, it's very sad to see it. This is a typical picture of what an explosion in a petroleum refineries. I always tell myself that I am fortunate after working in this environment for more than 40, 50 years. I've been fortunate to be alive and giving this little seminar to you. Now, this we went on to the concerns of management. Now we have gone to the next group of managers, but they are very qualified. And then we come to the design.
Sir, voice is not coming, sir. Hello. Sir, Krishna, sir. Hello. Krishna, sir. Sir, Krishna, sir, voice is coming, not coming. Hello.
Hello.
Sir, voice ಬರ್ತಾರೆ ಸ್ವಲ್ಪ ಆಗ್ತದೆ.
But I'm talking loudly.
ಈಗ ಕ್ಲಿಯರ್ ಆಗಿ ಕೇಳ್ತದೆ. ಕಂಟಿನ್ಯೂ ಸರ್, ಕಂಟಿನ್ಯೂ.
Pardon?
Continue, sir. No, continue.
Okay. Is my voice clear now?
Yes, sir. Yes, sir. You can continue.
But I did nothing, I was just talking. Am I too close to this computer? I don't know. Please
okay,
let me. Yeah.
Okay, sir. Okay, no problem.
It's all clear, no?
Yeah.
How long you miss this? For about 5 minutes or just a minute?
No, just a minute. No problem. You can continue.
Yeah, I'll just repeat it. The design group has told that the concerns we are having is the material data sheet. It is clear that this is a hazardous and toxic liquid. It is imperative to bring out hazards by formal and structured hazard studies. The voice is coming.
Yeah,
Hello.
coming. You can continue. Voice is coming, sir.
Yeah. Okay. Leaks of liquid is dangerous, and its vapor known to travel and cause vapor cloud explosion. I've talked to you. Now, point number 4. Please note there has been record that the liquid A pump has exploded because the liquid A pump was moving only inside that pump, and it has caused an explosion. And they say we have values. It says 6 into the 10 to the power of -3 occurrences per year, which means 6 failures in 10 to the power of 3 years. Okay, this is the kind of dangers. It is noted for doing hazard analysis and drawing up the fault tree. Knowing the liquid is a hungry chemical, it reacts violently with liquid B. Therefore, this has to be borne in mind to extract such a scenario during formal hazard studies. Now, we are going to do some hazard studies together, and these points will be noted. And they also talked about the churning and explosion again. Then they say, after doing all that, point number 7, we are all going to meet and then going to do a hazard study and bring out all the dangers. And then what we do is we look at the layer of protection analysis, which is called LOPA. We remember Mr. Srikanth had told you LOPA, LOPA, he was explaining. So we have to look at a sheet like that. Another leak is vapors leaking from liquid A system can ascend. Okay, vapor cloud I've talked about. They also said that we need to have the gas detectors to be installed in the plant for liquid A vapors so that we can sound the alarm. And also from the chimney of the plant, the vapor cannot go without getting steam bombardment on the vapor so that it will make the vapor into micro droplets so that it is of no danger. Up to point 11. Professor, is the audio okay now? Up to 11? I'm now going to start the. Please interrupt me whenever you want. No problem.
Okay, sir. Okay.
Now you have seen this simple problem. Sorry, the diagram. Storage pump reactor. Now all of us have met, and after 2 to 3 days, we have come out with all our little problems, and we try to improve this. We know what is the objective. A and B have to react. A is very dangerous, and we have to have the product C. Okay, so we made some development. So all of us sat and did the basic development. They said, okay, we need A, we need a pump, we need a valve which can be operated by hand to start with, and then the reactor. We have to also see whether we can have a relief system. That is, the chimney has to be there properly, and we have to also show it as a relief devices. Some valves are the relief valves and the chimney, all that. That is, the vapor should not go anywhere out except to that cistern, eventually to the chimney and out after steam. Then you are given a pressure indicator and a temperature indicator, and the operator is trained. He says, you tell him that operator to control pressure of reactor by throttling valve and controlling pressure, temperature gauges are available. Operator has been instructed to shut down if the pressure goes above 45 psag and temperature goes to 135 and above. Control reaction, the normal healthy control reaction is 30 psig and 120 degrees centigrade. Then the group decided to make a very stringent comment. They said, can an operator do this 24/7? Man is sitting there, however well he is trained. These 2 gauges are kept close to him on a probably simple panel, or it may be even a control room, and then this valve has to be manually operated. And if it slips for a second, and puts more of the liquid going inside, then there could be violent reaction and anything can happen. So this is unacceptable. That is, you have come to a decision saying that you need a basic control system, basic process control system. You remember what Srikanth had written? BPCS. So we want to look at BPCS. That is the first level where the control will be taken by a control room and a valve, etc. Well, let us look at that. The mechanical engineer and the chemical engineer also came and they added some more points. So we are going to see that. Right. Then we came and I'll go step by step. The first thing the mechanical engineer and the process engineer said, since the liquid is little bit dangerous and you say the liquid may get hot, he said, let us put a bypass line to the storage and also have a cooling arrangement, which I have not shown. So then they said that will make sure that the liquid never gets hot, or at least it gets, by heat exchanger, etc. So they took their part. Then came the instrument guys. The instrument guys did what is known as a hazard analysis, sitting along with who are the people who attend the hazard analysis? The people are, one, the process engineer, two, most important, instrumentation control engineer, he has to be there. Then mechanical man, piping man, and depending upon the kind of job, electricals will come in, some other specialists will also come in. So and you know what a hazard study is all about is they line by line, step by step, and then they say that what happens if the pressure goes high? What happens if the flow goes high? What happens if temperature goes high? What happens if the pressure is normal? What the flow is normal? And when temperature is normal? Then they look at all the control systems. They look at mechanical, electrical, everything. And then they say, okay, what happens if the flow is zero? Okay, next question. Someone says, what happens if the flow goes this reverse way? So it goes on and on. So to cut a long story short, what they said is, we need to, first they advised that we need a BPCS. A BPCS is an independent control group. I've drawn it pretty bad, but you have to accept the principle. So the reactor pressure is sampled by a pressure transmitter and the output goes to a pressure controller in the control room, let's say, and the output comes to throttle to move this valve up and down, okay, because it's controlling by pressure. Now, if you ask me flow control and all, we will not talk about it. Right now, only pressure control. So then they asked one more question. Suppose the pressure goes high. Another man said, we are still doing the analysis. At the time of analysis, so many things came. What happens if the pressure goes high? I say, you don't have a single protection. No, I have got alarm because the operator will see that. So what will the operator do? Operator will shut this valve. Which valve? This is that green valve. How will he shut it? He'll shut it from the control room or he will have a local control. Okay, not acceptable. Not acceptable. So the committee said no. Then the committee said we must have another protection. Then one more man in the committee has told, no, I want to have a totally independent watchdog. Nothing to do with this green fellow. So then he says, when the pressure goes high, this reaction has to be stopped. So I'm going to have a pressure switch. That is a pressure sensor, which has got also a switch inside that will speak to the logic controller. That logic controller could be a PLC, it could be a relay circuit, whatever, and that will give a signal to this red valve called XV and shut it. So now we have established that you need to have an independent pressure switch connected to a logic solver, which is a PLC or a relay panel or whatever you call it, and then the output goes and tells XV, please shut. So they have all been given a status of the diamond. The diamond which is drawn there represents the logic. It represents interlock, logic solver, association, and connection. I will lump everything together to simplify because this is only a mock discussion. When I go to the next set of slides in part 2, you will see them in real life how they look. So, okay, you have done this. Then the hazard analysis people said, what happens if the pressure goes low? He said, no problem. Then they asked, what happens if temperature goes? Oh, you need to have an alarm. Okay, we'll put an alarm. I've not shown it here. Then what do you know? No, someone said, no, even that should be treated with respect. Let us shut down the thing. Okay, we'll shut down. This I've not shown you. Then they said, now let's come to flow. When it comes to flow, what happens if the flow is excessive? No, I don't want any excess flow. I want a normal flow. Why to put excess flow? The reaction may become violent. So we can control. He said, okay, I'll control the flow. And then I'll do this controller, some magic. I'll do the algorithms and make it into a cascade controller and so that it will take care of pressure and flow also. Okay, I won't confuse you people on that. Go for a cascade control or something. Because the message I'm giving you something else. And then he says, what happened to normal flow? Why we talk about normal flow? Then they said, what about no flow? No flow, there is no flow. Okay, the valve will shut. Okay. Then someone said, we have to follow the hazard and operability study sheet. In that format, it's written, what happens if there is reverse flow? That is from the storage to reactor is a forward flow in this black line. What happens if the flow reverses? Everybody jumped from the chair. Why? Because if the reactor, which is partially converted, the product is this liquid is coming slowly, and as it forms, the intermediate compound is formed only after 2 hours 45 minutes, as I told you, 1 hour 45 minutes, whatever it is. The liquid C will be formed. Then everything is dead. So what happened? It so happens that the operator has controlled this so badly, he's kept the pressure very high, higher than this pressure, and this flows like this, goes into the pump, goes in, and what happens is you got, suppose it's a 1 ton storage of liquid A, it will react, and the area include maybe that district, that area wherever this factory is situated will blow up. That is the danger of reverse flow. So they jumped and they say, we have to do something about the mechanical man said, we'll put a non-return valve. I've not shown you a single thing. And I will show you what we have done as instrument people is we put a low flow sensor. There are pressure flow sensors, which I have not shown you, but I only showing you the critical one belonging to the diamond family. So this is the we have put. Okay, then we were satisfied. We got points in that, okay, we have reduced the risk so much. We all got points. Like you people get credits in the university, we got points. Because each time you do something right, you will get some points or credits. And then we go, and still the hazard analysis is not over. Then they say, hey, what about this? We have not come to the pump yet. So the pump, they said, what is the most dangerous thing? We said high pressure, low pressure, this pump not running, electrical voltage failure, all that we have done. So then someone said, hey, we have got a problem. You remember the churning of that liquid takes place when this pump is running and not able to deliver for some reason, that it forms, it gets into heat. And I said, that 6 into 10 to the power of minus occurrences per year, that means this pump has exploded because of the heat and then that liquid air inside it. Then they said, okay, we have to put. Then we did some calculation and all that, and we finally arrived at, we put 2 sensors. Why 2 sensors? Redundancy. And then one sensor is based on a thermocouple principle. The other sensor is located very close to it, and it is a RTD or a resident temperature detector, that is like a platinum thermometer type. Okay, whatever it is. So we have done this, and then let's finally arrive at the logic. We did some calculation, and we found that the reason we have concluded quite happy, but then we did some fine tuning and we found that the figure of the chances of explosion in this was coming to some figure which is not acceptable. But I'm not going to go into fault tree analysis, which we did, but you pretend that you have done it, and it came to a figure. I'll throw some figures at you. We wanted to get a figure And it is not unrealistic, it is realistic. And I'll tell you why. So we got a figure 10, we want a figure as the chances of an explosion in this unit is 7 explosions in 10 to the power of 7 into 10 to the power of minus 7 years. So many 7 occurs in 10 to the power of 7 years. That is the aim. In our, all this, what we did, we finally got a number which is, just say, forget it, put any number, 8 into 10 to the power of minus 6. Not acceptable. The chief of the hazard and operability studies and Hassan, we rejected. Then he said, come on, go back and do your homework and bring the credits which you pocket like the academic students, get more credits. And then we found that we have to introduce 3 pressure switches instead of 1. Why? Because we said we are going to introduce what is known as a voting system. A voting system means what are you trying to do? What are these pressure switches supposed to do? When the pressure goes to 45, it should shut down the system. What is shut down? XV should close, this pump should shut. That's the job of the logic controller. Now, having said that, see, you got 3. Why are you putting 3? Because each switch has got its own inclination to work or not work. That is, there is a thing called probability of failure on demand. What is the demand? Everything is 30 psi. Suddenly it goes up to 45, like a flash. And when it goes to 45, then it is supposed to behave and say, yes, please shut down. It tells a logic controller. So suppose that day, to your bad luck, it does not do, then there's a hazard or catastrophic action can take place. So we gave this 2 out of 3 voting system. That means this has to say yes, this has to say yes, and then only it will happen. Why you say 1? Why not 1 only or 2 only? Because there is a study called voting system, which I'm going to show you in the end. That is the first one day, it cleverly told, please shut down the plant. That was spurious. It was not called for. And then they shut down the reactor. They made the nitrogen purging, everything, and then now using so many dollars, then they started and they found this is a false trip or spurious trip. We don't want that. We want a real trip. So because these can fail, this can fail, this can fail. So the 2 out of 3 voting system, you're going to see that is the best mode. So we wrapped up this plant and gave it to them, and then they produced that stuff. And everyone was happy. So this is the end of this particular mock design, which I talked to you. Professor, have I made myself reasonably clear?
Yes, sir. Yes, sir.
Yeah, it's reasonably clear. That is, I told what is the end product of our discussion. Like we have the end product of the reactor, we have the end product of this discussion. Incidentally, there was one thing which I forgot to tell you. That is, this reactor is only reacting at 30 pounds per square inch pressure, and it can explode. So what the mechanical engineers have done, design engineers, they have designed it for 55 bar ultimate breakdown pressure. That is, it will the reactor will crack up only if the pressure goes to 55 bar, whereas we are operating almost around 2 bar. So there is so much of margin they have provided so that it will not explode. Right. Now, I'll tell you what I told you while it is said as fiction. Let me, with your permission, tell you it is not fiction. It is almost a reality. I worked on this system. I worked on this system in 1987, and I really insulted the system by drawing a diagram like this. There's no secret with you. A is equal to ethylene oxide, B is equal to nonyl phenol, and C is equal to some particular product which I don't remember. Reality. The values, the hazard and operability study, I was very much there during this. And gentlemen, you can understand how many trips I've shown you. Only 2: pressure switch and temperature. The number of interlocks, that is which belong to the red diamond family, were 25 or 30. Unless they are satisfied, you cannot start the reactor. With this, I end the mock design discussion, and I'll proceed to the next slide. And why I did this, people can appreciate the things that are coming in part 2. I think, Professor, I made some mistake. I have to share again. How do I go about it?
Again, go about to share, sir.
And to share, how do I get that icon? So I put the 1 second. Yeah, okay, I'll share now. 1 second.
Okay, sir. Okay.
Yeah, just see it's underneath. It's gone underneath. I'll just get rid of this.
Yes, sir. Now coming, sir. No problem.
Yeah, it's now it's okay. Coming.
Yeah. Okay,
Yeah,
sir.
okay.
Okay.
Audio clear, sir? Sorry, I'm asking you so many times because I
Yes, clear, sir. Clear.
the audio is clear and even the pictures are clear.
Yeah. Both are clear.
Now, now we go to the serious stuff of one of the reasons I talked to you on this kind of a vague story is because you will be able to appreciate the terms and definitions. Some of them are quite heavy on your mind and uninteresting, so that if you relate to that diagram and the little process that we studied, it will be a lot more comfortable for you. That's why I did that one. Now, what is your synopsis going to be? Like, 1 second. The synopsis is one we have already finished, and we go on to the next one, is a risk, layer of protection analysis, BPCS versus SIS, which Srikanth explained also very nicely, safety instrument function, safety integrated level, standards, design aspects, and types of proof testing. I am now quite happy because I have explained that story of that fictitious or hypothetical plant to you, because I am confident that you will be able to associate every point with this one. Right. The first point we have to talk about here is risk. This I don't want to talk to you because you are already been covered yesterday. This present environment is seen as multidisciplinary engineering and increased system complexity, and hence a growing need for all engineers and other professionals involved in process engineering to be aware implications of designing and operating safety related systems such as safety instrument system. Now I'll take you back to that diagram, which is a very queer and not a very well drawn diagram. But there, what we are divided with this group of engineers is that, do you need an instrument system? First, we proved that we cannot manage without an instrument system. So we were given go ahead to go with the basic process control system. Then we did a debating and hazard study, and then we came to this point and said that no, even this is not sufficient. We have to go for the next level. And the next level is your safety instrumental system, which is an independent watchdog. And that's all the topic is about today. Right. So that is a safety instrument system. Knowledge of relevant safety standards is essential. I labeled all the standards for you, which are important for you to know. Safety instrument system play a vital role in providing protective layer functionality in many industrial process systems. Now let us talk about this protection layer. It's like this security people, they've got that tier 1, tier 2, tier 3 like that, which you're all familiar with. The security system we are talking about is, as far as the plant is concerned, the core is the plant. The first level is by manipulating of valves and looking at alarms and looking at mechanical devices which are not instruments. Then we have to manage the plant. And then if that is not possible, we go to a BPCS. And after that, if that is also not possible, we go to the safety instrument system. And even that goes on. That's what this protective layer LOPA is about. We are going to see that diagram. That's what he talks about, protective layer. So he says that safety instrument systems play a vital role in providing the protective layer functionality in many industrial process automation systems. Need for safety instrument systems, managing and equipping industrial plant with the right component subsystems for optimal operations efficiency safety is a complex task of safety systems engineering. Now, the safety system engineering is a disciplined, systematic approach which encompasses hazard identification. We identified the hazard. The pump churning will blow up the place. The vapor cloud explosion will take place. And then we also said that on high pressure, the reactor may also fracture. And you may get a reverse flow, hence protected. So we had identified all the hazards in that little plant, hypothetical plant. Safety requirement specification, this is very important. It's called an SRC in the engineer's language. When you go to any consultancy, Tata consultancy or any place when you do this kind of jobs, Reliance and Engineers India and the top consultancy firms, they'll say, they talk in code language. What about SRS? The SRS is safety requirement specification. That's like a big book they'll give you. So safety systems, then you say when you have been told today that you have to have a safety instrument system for that small hypothetical plant, how would you go about it? You will go about it in a very systematic way. That is called, it is nothing but in philosophy, concept to commissioning. That is, you conceptualize, you design, you build, commission, operate, maintain, and last but not least, when the time has come for total upgradation or discarding the plant, you have to write a procedure for decommissioning also. To sum up, one can say concept to commissioning of the life cycle module. Now imagine for that little plant that we talked about, we put all these conditions, it will apply because we have fulfilled all the conditions in that. Maybe in a haphazard way because we cover all that in half an hour, which is ridiculous, but the principle you people can absorb without a problem. Now, this is where we are. When we were talking about this design, we said that we need to we start with this, red, okay? Hazard and risk assessment, process hazard analysis, safety integrity level analysis. This is a very, very word which comes everywhere and it's a deadly one to deal with. I need at least 2 hours to explain. But today I will give you a sample of the safety integrity level. You will keep hearing it every time today. That is nothing but it gives you an index of how the safety instrument system is performing. It's a statistical value. It will tell you that it gives you a number, SIL 1, SIL 2, SIL 3, SIL 4. SIL 4 is the gold plated. SIL 3, slightly lower order. SIL 2, slightly lower order. SIL 1, the lowest. That is in terms of a reliability or performance points, it gets the highest. And SIL 4 is not talked about because to build a plant with SIL 4, people will lose every bit of money in that. That's not done except in atomic reactors and all that. No one goes to SIL 4. Up to SIL 3 is okay. So this SIL, don't get worried about SIL. SIL is nothing but a kind of a safety performance indicator or statistical representation of the performance of safety. That is when you want it, it will work. What is the reliability, etc. All that is built in there. Okay. Did we do that for that small plant? Hazard and risk assessment? Yes. Did we do a PHA? Yes. Still, let us pretend that we have done it. We will not talk about it. Then we are going to the design, execute, and did we design? Yes. We put pressure switches, we put temperature switches, we put valves, we got that red diamond programmable logic controller, and we got the trip logic, cause and effect diagram, all that. Then let us go and install it. We install it? Yeah, tomorrow we install it. We'll commission it? Yes. Now, let me talk about this commissioning. It gives me nostalgic memories. When I commissioned, this was, design was done in the US, in a place called Wilmington, where I was involved in the Hassan also, and the plant was in Bombay. So I was fortunate to also be in the installation commissioning when we did. The total amount of ethylene oxide which had to go inside 2,500 liters. So what happened was that everyone in the control room was counting backwards when it reached something like 25 liters. And then it had to reach zero and it had to shut very safely because the batch is over. Fortunately for us, our team felt happy because it did the job first time right. So that was a joy we got from this reactor. Deadly reactor, it won't allow you to start unless you fulfill 25 conditions. Right. Coming back to reality, installation, commission, validate whether everything is right, and post-commissioning work also do. What is FAT, or most of you may be knowing? Factory acceptance test of the logic solver and the sensors, etc. What is SAT? Site acceptance test. After we do all that circuitry integration, we have to do that. Then this one, I'm reserving it for the last. Functional proof test. Okay, that we have done that because the sensors are working, valves are working, etc. But it has got a very important aspect, which I'm going to give you before I finish this discussion. Then operation maintenance, yes, I'm continuing to do, because let us say we have worked for 3 years, some modification you are doing, all following the same path. The safety cycle, hazard and operability studies. Don't take shortcuts. Otherwise, what happened in Fixborough? They did something, hasty modification, and the plant blew up. So it's not allowed. It has to have so many signatures of A, B, C, and a hazard study. Each pipeline line length of, say, 3 feet is hazard analysis we have done. Otherwise, you cannot get a modification through. Modification done, then we go back to square one. Then one fine day, after, say, 20 years, they want to decommission. That's why actually some of them call this safety cycle in a very light-hearted, sometimes a crude way. They say it is from cradle to the grave. That is the cycle, safety cycle. Okay. Next time, not touching, it's for you to read, because this is the pure, that is the symbolic safety cycle. This is for you to read when you get time. And this is the International Electrotechnical Commission. Most of you will be knowing this 61508 safety cycle model. So please go through this. It'll tell you what are the steps we take for the concept of commissioning. And it's very, very user-friendly to understand. And it will give you a lot of inputs in case you want to teach this subject sometime. Right. Now we go to risk. And the risk is, in that case, what was the risk? The risk was that you did not want the neighborhood in that hypothetical plant, the neighborhood to blow up, and you don't want any vapor cloud explosion, etc. You've taken care of. There is a figure for that, which you are going to see also. So the top management sit, technical people, they are not only the director, people who may not be so sound in this technical, top technical people meet, and then they say, okay, let us say class risk 1, risk class 1 risk, class 2 risk, class 3, class 4 risk. Now, which one we take? Class 1 is totally unacceptable. And let us go to the next one, 2, 3, etc. So we selected some value, let's say class 3 or class 2. That doesn't matter. So you have selected the risk. And then the question there is very much is, can you eliminate risk? The answer is no. Because they'll say, no, it is impossible to eliminate risk because it is not a practical thing. If you try to solve there's still something that will fail because you don't have 100% truth. And we won't discuss this because this is discussed threadbare in so many places. So risk can only, then what you can do in that same hypothetical diagram that we saw, we have arrived at a risk without anything. That initial figure that we saw, we found that the risk is 100%. I'm just using some loose words to show what the risk is, 100%. No one gives risk like that. Risk is given a number of people dying in 1 year, etc. So let's say 100% risk. It was full of risks when you saw that first page. And then what happened is, by doing all this, not only instrument people, there are mechanical, civil, and the electrical, and all other disciplines put to process people, the operating instruction, everything put, then that 100% risk, what we were prepared to accept some risk level. So they reduced that risk and brought it to some lower value. Let us say they brought it to see a diagram also of that. So then what is the instruction for you to during design is, there is a very interesting, catchy word called go by alarm. Nothing clever, as low as reasonably practical. So you have reduced the risk. You cannot eliminate. And you have to also look at the purse. You cannot go in a senseless way, only looking at the technical. You have to look at the economics, the operation loss, the operation shutdown value. The operation shutdown has got a value. And hours of production has got a value. If you shut down a plant for nothing, you lose billions of dollars for nothing by a pressure switch, say. That's how you got this voting system. You don't want spurious trips. Then you go to the next step. Then we go to this diagram. It says that we go intolerable region. That is non-process risks, and then broadly acceptable region. It gives you this band with which you can play around. Fatality rate, everything is boiling down to how many people die, because they give the highest value for that factor. Okay, so this is how an alarm diagram looks, and you have to pick a point here and get it approved by the management. It's not that instrument man will approve it or the process man will approve it. It will be approved by the top brass who are knowledgeable on this, and they have international data to compare. So now we are trying to do, there are a lot of mathematics in this, and that's the last thing I'll do in this kind of a course. It's only overview. Risk is a function of the probability of an adverse outcome, and is the most important thing here. Probability alone will not solve the problem, because you'll see it for yourself. That is, risk is a function of the probability of an adverse outcome. Let us say people dying or a fire, and the severity of that outcome. So if you have the event taking place and there is not much of severity, suppose you have a cooling water pipe failure in this front of the road near your house, and you find a lot of people's houses have been flooded, etc. That has happened because that pipe has failed. But then what happens is, that has not caused a concern of people dying because of into these toxic gases or something like that. So the consequent factor is very, very important to understand. Probability that it will happen and consequence. What are the consequence in our little plant, hypothetical plant? The consequence is pretty bad, because it will blow up the entire vicinity, and also those residential areas may get affected. So the risk level is high there. Suppose you made the same plant in the desert, at least 100 miles, nobody, there the risk is very less, except the operators who are there. So the consequence there will be less. So consequence is the direct effect of an event, incident, or accident, is expressed as a health effect, death, injury, exposure, etc. And all of you are aware, I'm giving you the tabulation column, which I'm not going to project it. I told Professor Prasanna, I added it on with the presentation slides are given to you. I've added one more tabulation with 10 deadly accidents in the world, because I don't want to show it here. It will take a lot of time. And you can see for yourself why we are discussing the safety instrumented system like this to a group of you senior people who are in academics and with rich experience. Maybe many of you are from industry also. Why we are discussing, it's all because of that tabulation column which will be given to you. Then the Bhopal is there, Clicksborough is there, that other atomic what's that is, I forget the name, that is also there. So all these items are there, and all that put together with the debate in 1974 brought in the focus on safety. And then, before we go to the next slide, the most important point is not the safety philosophy. Safety philosophy, yes, very, very important. But now the world has shifted to, yes, safety, you saw the definition. That's how I started the slide. It is the risk. Everything say risk. Suppose you have to put a plant which is going to give the country so million rupees, dollars, crores, whatever it is, and then you're a group of trained professionals. Where you are also told in the process narrative that this will explode, that will explode, this will catch fire, that will. Will you run away and say that no, we can't put it? Then you're not a professional. A professional will say, I will decide how can I reduce the risk, and also make sure that fatality, if it comes, it's only category 2 or category 3 or 2 or whatever it is in the risk chart. That is the way professionals work now. Nobody will run away. They go scientifically, and thanks to 1974, the entire hazard studies process, Hazan study, that is even more interesting. We did the Hazan. When I did this reactor job, in a group of the people in our company there, the headquarters, there we did a Hazan, and every day the suspense was, we did what is known as a poultry. You people must, some of you academicians must have used it very much. But there we were waiting for the last figure. What did we get? What? Oh no, God! It's got to still not a satisfactory. Then we did jugglery of the redundancy and then diversity and putting parallel trips and removing this logic solver, putting something else, and got the marks finally. So that we were happy. So that's the way being done scientifically, not by pure guesswork and say, no, you put two valves instead. If you put two valves instead, you're also inviting trouble. Because if you put two valves or two pressure switches or two logic solvers, they come with a baggage also. They come with a baggage which is it's got its own probability of failure. Where one pressure switch will fail, we've got two, that will also fail. But maybe it's a gold-plated pressure switch. But the point is, it's also coming with a baggage. It doesn't say that forever I will work properly. So these are all points which we have to think when we go for voting and other matters. Right. We talked about risk. And this is an interesting diagram, and I don't want to explain it because I can't explain better than what's drawn there. Then this we come to, I just wanted to take a mental snapshot only. This is very important. Risk, now we have been talking risk loosely, So when you get time, when you go through this, once this chart comes to you, please read it, and I'm sure you'll be able to analyze it even better. The risk classification of accidents, table B1, is an official document, IEC 61508, chapter number 5, suggested example adapted to hypothetical industry sector. Catastrophic, critical, the matrix is made so well. So 1 per year is, what is it? It is the critical category, etc. So if you say 1 per 5,000 years, it is catastrophic range, it goes down to 4. 4, I think 1 is the worst case that you're going to see. The worst intolerable one is that Roman figure 1. So this table will give you a lot of education in this, instead of my trying to explain it, which I have not add values. Right. Now we come to, you've understood risk, and you've also earned your living to get BPCS. What analyzing and saying that coming back to our own hypothetical plant is that valve cannot be turned either from the control room by remote or locally by an operator looking at 2 or 3 instruments and say, no, I will manage the plant. That will be most foolish. And we proved that BPCS alone cannot do, that's that green pressure transmitter, which you saw in that picture, and the valve, it cannot do the job. So we graduated after earning our points and say, okay, now you're allowed to go into the BPCS is done, and BPCS is safety methods employed to protect against or mitigate harm, damage by alarms, etc. Alarm and the pressure will send. Again, that valve which you saw, control valve which you saw in that, I'm not slide back, but you can remember that the controller output went to a control valve. Now in the hazard analysis also, they'll say, if the valve fails because of the air pressure failure, like a power failure, what happens? The valve has to shut or open. We have to configure that. And we'll say, yes, it has to shut. In some cases, where cooling water is involved, cooling a reactor, what happens if the instrument air fails? You'll say the valve must go into open position. So all the configuration is all part of the hazard which we do, and the operation include. Now, control system, BPS, safety methods employed to protect against or mitigate harm, damage, etc. to personal, plant, and environment, and reduce risk. Changing the process or engineering design. Risk, how you reduce risk? BPCS, change the design, do a good mechanically integrated system. What did we do there? We brought that reactor and we said that it will fracture only at 55 bar. Then the process has been also tweaked by the process engineer, developing, train your operators so that they don't do the wrong things. I think we have to go fast. Now, this is your general concept of risk reduction. You're starting with the initial equipment under control risk, like that plant which we saw. First, that hypothetical plant. Then the first is risk reduction from safety instrumented system has brought the risk needle up to this point. And then they say risk reduction from other technologies, secondary level safety systems, etc., that we may be using some other methods also, even mechanical, maybe put some two relief valves, we don't know all that. Then risk reduction from external facilities, like you make sure the reactor is nicely covered so that if it is exploded or the gas leaks, the gas is treated from the local environment before it goes to the chimney. Many things like this. So this is the, and finally you get the residual risk. The tolerable risk alert is marked here. You have done a better job because your residual risk is only so much. Up to here you're allowed. So this is your good job, your actual risk reduction up to here. So you're all now familiar with risk reduction. We talk about that hypothetical part every time. Keep that in mind so that becomes easy to follow. This is what Shrikant had told you yesterday, and I'm not explaining it further because in principle it doesn't depend only on safety instrument system. There is a relief valve system, and then after that you got where you can contain the explosion. Sorry, the gas remove. That is done, and then if it goes beyond your capacity as a plant manager, then it goes to the national disaster management system, etc. So you do your part up to them, and then beyond that, if it's such a tragedy, then some others have to take this. So you design that with a good risk reduction factor and good material. You should not get into it. Now, this is another diagram which doesn't, for you people, it's not a very big deal. The only thing, it's more picturesque. And the brown one means it is not belonging to you. It belongs to the other people. They're mechanical, chemical people. They put a relief valve. In this case, the FIC belongs to you. The green is yours. And then the pink is all emergency level switch going on to a valve. Okay. And then this is a level switch, is the alarm level. And then next is your trip level is pink. This is your assist shutdown. Right. Now, yesterday when I was talking about control valves, you remember I talked to you about the linear valve and then the equal percentage valve. But there's one valve called quick opening. Now, in the case of a shutdown valve, this valve has got only two jobs: fully shut or fully open. And when it's fully shut, it should not leak. So this is a trip valve, is either yes or no. It's a binary 0 or 1. It doesn't do analog duty. It is absolutely shut or open fully. That's called a trip. And I don't have the time, but I can tell you the timing of closure is also very important. I worked on that, but today is not the time to talk about it. I worked on valves which have to shut within half a second or about 1 second. You cannot believe, but it happens. And it has been done because if you don't do that, you will probably corrupt something in the reactor. 1 second, you will not believe, half a second, 20 seconds, 5 seconds, this kind of is a closure time. Now, I will not take any time on the BPCS or the SIS. I will take you straight into, this is how, this is like a kid's diagram to show that this is your sensor, this is your logic solver, and this is your final control element. Okay, this is not a big deal. This is showing you both together, and you're already familiar because in that diagram, however imperfect it has been drawn in that first part of the presentation, you saw that there is a green PT and a red diamond. Here, the safety instrument system has got a separate PLC, and this BPCS has got a separate. This is how the other things, interfaces, power supplies are shown. Nothing different, is independent. Now let's go to this. It's now 1:10. I got time up to 1:30. Right. I want you to just see the complexity of this. We are not going to discuss too much. This is basically a dual. This is a furnace, and you're going to fire a gas supply in this, and you got oil supply on this. And this is, I'll explain to you, this is called pilot gas. Now, this is a very, very good example of a safety instrumented system, which is now controlled by a PLC. Good old days, it used to be controlled by a relay circuit, now by a PLC. Now the PLC here is safety PLC, is a gold-plated PLC. Why it's gold-plated? We can talk for 1 hour on that PLC, but today is not the day for that. For example, you go for Tricon X, triple modular redundancy, that it's got a voting system built in for everything. Power supply, you got a dual power supply, and you got where and card input card is one, there are 3. But everywhere you've got voting in this, and it. I'll give you an example. One, I'm talking about my design days. This way goes way back to 2000. No, sorry, not 2000. 2000, an analog input card for a normal PLC would cost something like 10,000. And don't take the figure too seriously. But then the analog input card for the safety PLC would cost almost 6 times or 8 times. That is the beauty of those PLC. Reliability, higher SIL factor. I told you SIL is an example of the safety performance. We'll talk to you briefly on SIL. Now coming back to this is you got a low pressure switch, you got a shutdown valve, you got another shutdown valve. We are talking about gas. And then this path goes here. Let us go to the oil. Oil is also got the same. Shutdown valve 1, shutdown valve 2. Why? Redundancy. If one fails, the other one, we should not expect. Suppose this fails to close, then you had it. So you got 2. Then you will ask me a question, what is this in between? This is what is known in safety instrument system, a very, very popular term called block and bleed system. Okay. Now, the block and bleed system, in the gas, you don't want the gas to be trapped here. So what they do, particularly for gas, it is relevant, closes in an emergency, and this opens, it goes to the ventilation. That means this pressure is depressurized by this system, by 3 valves. Okay, this is another pressure switch, and this pressure switch, the status of the pressure. Then you will ask me, what is the reliability of that block and bleed system? How do I know? Yes, this is connected to a PLC, this pressure switch. It's depressurized, it'll show it's 0 because it's done the job. So that signal, it goes into some other circuit, etc., etc. So it is the safety instrument system, repeat, sensors, then you got logic solver and final control element. You got sensor, this is the sensor, then you got the logic solver, which is not shown here, and then your final control element here. Now, it's fired by gas, like our domestic gas, or it's by oil, and you select it by a selector switch and go, and you fire it. But how do you start this safety instrument system? How does it start this system? It starts as follows, 0. You're going to this firing heater, and you're going to fire it. What are you worried about? You don't, what is the end goal? You know, there you wanted to make sure that the residential area in that plant that you designed did not blow up, and you did everything to provide you a safety instrument system. But here, what is the danger? The danger is any fired gas heater. This is a heater firing, and that heat is going to heat something else. You don't worry about that. It may be water, it may be a boiler, it may be some other hot oil. But this particular heating, if the fire is there, not extinguished properly, and the gas is building up, and the gas is ratioed, or the liquid, the fuel oil is ratioed, so that the optimum mix is mixing and going away, heating. If it is resident there and it gets into an odd combination, you could get an explosion. So when you start the fired heater for the first time, you have to first purge it. There is a cycle. Okay, I know that cycle. I still, my memory is not failing me. 0, start the blower and push air into the system. 1. After 7 seconds, you check whether there is a mischievous flame floating around there, because something is still burning. You don't want that. Okay, that is clear. Then you say, I'm going to make a small pilot flame burn. Here you got gas and an ignition transformer, which provides you a spark, and it gives you a small flame. And that flame is sensed by the flame detector, and it says, yes, the flame is there and it's quite stable. Little flame, it's of no use to you because you need a giant flame. And then once the PLC says, yes, this is a proven pilot, it says, then this particular oil mist which goes is the valves are all allowed to open, oil will go or gas will go, whatever be the fuel you're using, and then you'll get the main flame. And then the flame detector will continue monitoring and it will hold its hand on the firing cycle for about 105 seconds or 120 seconds to make sure there are no surprises. And once it is satisfied, then it'll give a go ahead signal to go on full load in your boiler or in your other heating aspect. So this is your safety instrument system, which is a realistic, not what I had drawn there. That is just to bring you into this is how it works. There are a number of problems that come here. In the least that is said, if you're a person who has been operating and commissioning it, you could write a lot of stories, and that's the last thing I want to do now. Right. Then we go to, you know that we start talking about a safety instrumented system, which is the BOSS. The BOSS has subordinates, which are called safety instrumented functions. Now, let us look at this particular thing which we saw. We saw that this is a, I would call it as, I'm not, okay, SIS burner management combustion control. Let us say I'll purposely call it as SIP. Suppose there was another burner like this, another burner, and there was a master controller also. That I would call it as a SIS, and I'll call all these things as SIP. That is safety, because they become the sons of those, the SIS. So a SIS can have number of SIP. And SIP is almost like, it's just nothing but a safety instrument system, but it does a function. Since one more, this function is protecting the furnace. The other one may be protecting a level, or another one may be protecting a boiler. So each one is doing a different function, but all of them may be operating on one super duper PLC, which is a SIS. That's one you have to do. This functional safety system, etc., is a very important definition for you, and it's better I read it. See, functional safety system is a term used to describe the safety system. See, there are several safety systems. The fire and gas, you've got some safety system, you've got some systems for spraying from a helicopter, so many things. But this functional safety system is a term used to describe the safety system that safety system is dependent on the correct functioning of the logic solver, sensors, and final control. There in that flame sensor, if the flame was not working, sensor was not proper, it may not be sensing, or it may give a false reading that the flame is on when the flame is not on. So these kind of things are, so the sensor, everything has to work as a proper orchestra. This is nothing but telling you what I told you. There's all these, one logic solver has got so many other SIP. And then each one has got its own tagging. Now, I'm not going in depth with SIL because the stuff I've given you is sufficient for you to understand. But please remember, SIL, I'm going to show you a chart of SIL so you know what SIL, how it is labeled. So SIL is actually a safety performance indicator, statistical. It depends on so many factors, and it's all written there. Now, very important point to take away from today's presentation is you've got a transmitter, you've got a PLC, and you've got another transmitter, 3 transmitters. Now, if you say that the first transmitter is SIL 2, the second transmitter is SIL 3, and then the other PLC is SIL 3, it represents the reliability of that particular unit you have. But if you go to our little diagram that we drew, if you want to give it a SIL 3 rating, all the items put together, and after calculating the probability of failure and doing all the calculation, the end product of the summation of this failure, that failure, everything put together, you may be using a manufactured approved SIL 3 pressure switch. That's a different matter. But if all of them are assembled, it doesn't mean that if you put the SIL 3 in your factory, the whole factory environment becomes SIL 3. No. That's most important thing to, and I have mentioned that and I have also underlined it. So SIL3 is your factor which tells you, yes, I'm very reliable, I'll work whenever you want. That's the kind of thing. It actually gives you the safety performance of the system, complete system, because of its presence. SIL level applies to an entire system. Individual products or components do not have SIL ratings. When you rate, it is capable, your pressure switch or transmitter is capable of operating in a SIL3 environment. Now, we will go into a little more detail and see this one, this slide, and then I want you to see this one. Yeah, this one we have already seen, but I want to read it again. When the hazards identification and risk assessment phase concludes that a SIS is required, the level of risk reduction afforded by SIS and the target SIL have to be assigned. It's very important for you to know because you have done it today for that small plant. Whatever I've written in red, you people have done, assuming we all work together in a virtual manner and design this. The effectiveness of a SIS as an independent protocol is described in terms of the probability it will fail to perform its required function when it's called to do so. That is the quality of the SIL. If I ask what do you call that, diamond XV to shut 100 times, does it shut? Say 99 times it has shut. Once it failed. Okay. The other one, 40 times it has shut. 60 times it has failed. So that is much more reliable. So it's got a better reliability stuff. Higher SIL. Okay. This is before I go to, yeah. Now, this I'm bringing you into some figures. So far we are talking about SIL and I was very loosely talking that it's got a reliability stamp, how reliable the safety system is. The SIL is an indicator. What does it contain? SIL, the highest, the gold-plated one, SIL floor, it says that we'll go to this high demand and low demand, I'll explain. See, when you say demand, is you go back to that your sketch, and in that sketch, you saw that the command comes because reactor pressure is high, higher than 30. Please shut. That is the process demand we are talking about. There are certain places like in your factory automation where you have these light curtains. I'm sure all of you know light curtains where the robotics are also involved. So the moment you cross that, it will have to do that shutting down process. So that is a continuous mode. So suppose we don't look at the continuous mode just for our own convenience. We say a pressure switch trips say 10 times in a year or 20 times in a year. So the low demand mode we'll see. So the probability of failure average demand that the safety system will fail if you have got a SIL 4 category, the rating of that entire installation with all the transmitters and valves, everything put together is between 10 to the power of -5. Average probability of failure is one failure between 10 to the power of -5, and that is between one failure in 10 to the power of 4, one failure in 10 to the power of 5 years. In between, it will swing the highest. What about this one? The lowest, 1 by 10, one failure, 10 by 1, 1 divided by 10, and 1 divided by 100. 1 by 10 and 1 by 100. How much of risk you have reduced? From so much, 100,000, you reduced to this much. This is a super duper one. Here you have reduced, identified and reduced so much. So this is the super duper one rating, and this is the, so suppose tomorrow you're putting up a plant, I'm showing you this A and B and C and all, you put an ordinary water treatment plant. You don't have to go for all these things. You can go, SIL 1 is open. So nobody is going to die in a water plant unless something drastic happens, something falls on him. By sheer process reaction, there's no reaction there. This is for you to read, and I'll have to come very close to the end. And this is all your standards. Please read it. It is very lucid. My reading it. This is very important for you to know the difference between 1508 and 6511. And 6.1, what this standard means, what this standard means. In the nutshell, they are shown, but it's got huge volume. They've got 7 chapters, and I think it's got 16 chapters. I don't remember. So one is more for system designers, integrators, and this is for the suppliers of those units. The standards, safety standards. The comparison is also given. Now, I don't think I'm going to only tell you this and close shop because the design is all given there. Now, this is a pressure switch, and this pressure switch operates in a manner like this. You know that plant we designed, that plant has got 3 pressure switches. Now, when you got that 3 pressure switches, let us say we take one pressure switch, you push ethylene oxide vapor or whatever reactor vapor in that, and then what happened? Here, you got the sensing element. Here what happened, there's a seal, there's a piston, and it moves inside the chamber, tight piston, and that triggers the micro switch. And when the micro switch is triggered, the switch is operated. So we designed the switch such that when the switch is operated, that is when the contact is closed, it is healthy. That is, the pressure is healthy. If the contact is open, when the pressure drops, in our case, for this example only, when the pressure drops, it's unhealthy. For this example, compare it with that plant we designed. So it's like this. No pressure, dangerous, healthy pressure, so okay. You can put it the other way also, but what I'm driving at is how many problems can it create in this switch? One is when the pressure is right. Let us say, don't worry about what I said about contact, closing and all that. Let us say 30 is your operating, 45 you don't want that switch to act. Sorry, you want that switch to act. 45 PSIG, the switch is acted today. Next day, tomorrow is Saturday. The switch is acted when the pressure was 30. Another case, Sunday. Pressure has gone up to 46. The switch is not active. So, I told 3 things in a very simple way. One is a fault or failure, safe failure. It was unnecessary trip the plant, but it cost your company money. The second one is a silent killer. You don't even know that the pressure has reached such a high state and it's sleeping. And no way you know, and it has spoiled the entire area. Okay, there are 2. The other one is a healthy one. That is, actually the pressure went high, it's stripped. So what is this? This failure is called failure to danger, failure to safety. Then in failure to danger, there are 2 categories. Failure to danger, detected, and failure to danger, undetected. Let us assume this is a complex, this micro switch, let us assume that the contact has got welded inside. Then how will you know that this devil is sitting there? Only by one way. That is called proof testing. What you do is you've got a periodic checking, and every 2 months you're checking because it's a critical thing, and you get permission to check it. At that time you find this is not correct. It is always engaged and showing green, which is wrong. So you correct it. That's called proof testing. I told you a chapter which runs to 3 chapters, a topic which runs to 3 chapters in 15 seconds. I got the message. There are 3 types of failures. Failure, safe, detected, and undetected. It suddenly tripped for no reason because the micro switch wire got loose. Safe. That micro switch is jammed and nobody knows. Danger. And double danger because you have not detected it. But today I'm walking past and I test it and I find it's in danger. It's luck. So that is danger but detected. So basically what we have discussed today is we did a hypothetical discussion of the plant, and we brought all these elements which we did in our second slide, second presentation. You use all those words which you remember, which we did that when we went through this hypothetical thing here, so that you are able to understand LOPA, you are able to understand the safety cycle, because we did all that there. And also SIL I mentioned, but actually I should spend more time on. I need another 90 minutes for SIL, which is not possible to get. Then this is a very tricky one. This failure systems is a very, very deadly one to know, and lot of calculations are there as you go on. And there's one more diagram I think you have to see. This is the one I talked. You all know what we said. The method of operation is written there clearly. The first one, A and B, too much of safety. A is failing one day because it has failed, spurious failed. Today, B is failing, A is failing, B is failing. So this is bad because anyone opens the circuit, it trips. Now here, you got in parallel, and then the availability of the CLC or the safety monitoring system is so good that even if truly the switch opens and the other one doesn't open, you have, okay, you got safety, but it may not become too much of availability. This is too much of safety, but this balance, two must say yes in a population of 3 is the ultimate. So I have covered, and I must thank you for your patience. And I felt internally happy that I've been able to transfer what I have covered in many years of my work to a group of esteemed teachers. And I think it's a rare privilege. And I'd like to close by thanking all the organizers. Professor Prasanna has been looking after me so well, and with all his colleagues and the higher management of the system, I say a big thank you.
Thank you, sir.
Thank you.
Hello. Thank you. On behalf of the Electrical Engineering Department, UVCE, thank you, sir. Before going to thank you, I said something about Krishna, sir. Krishna, sir, is ever been an eminent personality. Even though age of 80 years, he is explained well about control, walls, and safety systems. So what is his past 55 experience? He explains thoroughly, step by step, how to use the control wall, what are the parameters in the control wall, then come to the safety system, because safety is the must in any company or any organization. Without safety, we cannot run the system. The safety system is well explained by the Krishna sir. Thanks. And overall, we learnt about how to use the control wall in the industry as well as the final thing is the safety. Thank you, sir. Your eye-opening section to explain about these two things in the age of 80 years. That is our, we need a blessing from you, sir, to continue such these occasions in our life.
80 is only a number, Professor.
Yeah, sir.
80 is only a number, that's all. I look
No,
at
sir.
it.
Even for us, nowadays for 50 or 55 years, we'll die. But in the age of 80, your evergreen speech is going to give value for us, our life. Thank you. Thank you, sir.
Thank you.
Thank you, sir. Thank you. Maheshan?
Any questions from the participants? Hello? You can unmute and you can
I think they are
ask the question.
busy with this filling the feedback and other things, probably.
No, one of the participant asking Krishna sir's email ID.
Yeah, I mailed and number also I mailed.
Yeah, please give it to them. I'll be happy to interact with them and learn something together.
Yeah, I already given them, sir. In the chat box, I place your mail ID as well as the number.
Yeah, please. Yeah, no problem.
No problem. Later I'll contact you, sir. Thank you.
One question I have, sir.
Yeah, please.
What is a proof test interval?
Okay, very good question. Very good question. I like that because it is a sharp question. Now, for example, you have got a critical plant like that hypothetical plant that I showed you. There we have all met, and as per international rules and standards, the proof testing for that pressure switch, which you saw 3 of them, is, let us say, 3 months, once in 3 months. So the interval is, suppose you do it today, 3 months later, you have another chance to check it. And what you do in proof testing, you get permission from the control room and take a permit, and you also, at that time, it is bypassed with permission, and you don't take it to the what do you call that, laboratory. You do it there by simulation sometimes, but you do something else also. So the proof test is done in the prescribed, and that number is arrived at by calculation. It is not by, you see what has a very, very good question you asked. The proof test period is built in, like I told you, the university people get credit for, you do this course and you do an extra course on artificial intelligence, you get credit so that your value starts going up. In the same way, you can improve the quality of safety action by doing proof testing. Very good question. I'll tell you why. I just explained the pressure switch, which was failed because the welding of the micro switch has taken place. That test, you will never be able unless you do a proof testing. Proof testing is the savior, actually. And one more thing is, proof testing has to be done, as far as my philosophy, I've done it, practiced it, dynamically. You know what dynamic proof testing is? I'll take just 30 seconds to explain it. In a complex plant, you've got a turbine, you've got compressors running, belting out day in and day out. So on the 10th of October, someone told me, the plant manager told me, Krishna, the plant is going to shut down. Then I'm going to make a request. I said, can I shut it? This particular trip channel? He said, okay. So instead of them using a push button or some other command to the electrical section, we will simulate this particular high pressure drift by our own method and shut down the plant. That means you tested the entire system, including the calibration of the pressure switch. I've done this, and it is so, because if you do only the proof testing of the pressure switch, it is possible that the input to the PLC, something could be wrong. I'm just throwing out, if you do a proof testing, real simulation, you can prove the point. Absolutely, very good question.
Thank you, sir.
Thank you.
Any other questions from the participants? I hope there is no questions. Thank you, sir. Thank you, Krishna, sir.
Thank you very much. Yes.
There is an announcement for the...
next step, you can leave the meeting, sir.
You can leave the meeting, sir.
Okay.
There is one announcement for the participants.
Yeah.
Dear participants, the feedback link in the ATAL portal, it is open. Participants requested to fill the feedback link in the participant portal as soon as possible. Please fill the feedback in the ATAL portal as soon as possible. It is open now.
Okay. Apart from the feedback, when you're going to fill the feedback only, you're able to get the certificates. That we are going to submit the attendance certificate as well as your test marks. So before that one, at 2:30 we're going to start this session where the discussion for the 10 minutes, and after that one you're going to conduct the test. The test is objective based type questions. Don't worry about that one. I think already you come across the 5 days. Then after that one, you're going to have the validatory functions with our honored Vice Chancellor. Please be at the end of the validatory section, because afternoon session via attendance you're going to submit at the end. If you're going to leave that session, then there will be a problem to download the certificates. And I'm asking the participants to please join at 2:30 p.m. because we're going to log the meeting, because what happened in the first day inauguration, I don't want to happen again. So please join well in advance with the 2:30 p.m. and be at the end of validity sections. Within 1.5 hours, we'll finish everything. I think after that one, you may able to download your certificates after filling your feedback form, while you have to upload your attendance as well as the test marks. Thank you. We'll hope at 2:30 we're going to join again. And thanks for your patience from past 5 days. Whatever the problems occurred, you people are helped us to continue the program. Only in the morning session, I don't know, after applying the control only, the program is time to control. Okay, thank you.
Yes, sir. Flight controller. Flight control.
After applying some control application, our program is going to control. Sorry for what happening that in the morning session. I think after that one, you hope you are for the profession, your professions, our eminent speakers given a very good ideas. Thank you for that one. And at the same time, in the validatory functions, we are not going to call your name. Voluntarily, please come to explain your feedback about the program. I request you once again, please come voluntarily, explain your feedback about the program in the validity section, please. And while writing the test, you can switch on your video, not for the monitoring. You'll take snaps. Okay.
Photo session.
Photo sessions. Keep video on for the 1 or 2 minutes. We'll take some snaps and you can after that one we can stop the video. Thanks and have a good lunch. We'll come back.
Sure, sir. Thank you, sir.
Mayank sir.
Hello.
Mayank sir.
Mayank sir. Yeah, please, sir.
Yes, Mayank.
Yes, sir. You have to give feedback, sir.
Sir. I've already submitted feedback.
No, sir.
No.
Wait, Maheshan.
Validatory function.
Sorry, the validity function. We have the feedback. One feedback event is there. Please voluntarily come and you deliver your speech in the feedback event for 5 minutes. Voluntarily, please come. Okay. You tell about our organizing and our speakers, selection of the speakers and our program. Okay. Thanks. Have a good lunch and come back at 2:30. And because you have to write your test, have a strength now. Already went over the 5 days program. Thank you. Now I'll end the meeting. Before going to your lunch, please fill the today's feedback. Thank you. At the same time, if you time, go to the ATAL portal and fill the feedback forms. Okay, thank you. We'll end the meeting. Maheshan, will end the meeting?
Yes, sir.
Yes. Where is KPS, Madam Maheshan?
Sir, I'm here.
Oh, yeah.
Where?
Sir, even ask your friend Nageshwar how to give feedback.
Madam, that is left to them because you cannot ask particularly.
Anuj sir was one minute. Anuj sir was also the participant and the speaker. I think you can request.
No, madam. No. Wait, madam. We are not going to request because they should be coming from the art, whatever program or whatever the our speakers. They should come voluntarily and they have to express their feedback about the program. Okay. Okay, Maheshan.
Okay, sir.
Okay, KPS, madam.
Okay, sir.
If they are voluntarily not come, it means that one. Okay, we'll see that one in the voluntary section, validatory section. Okay.